Hello everyone and welcome to Chapter 14, Kinetics of a Particle, Work and Energy. This module discusses principle of work and energy. Before you start this module, you should be able to find the work done by a force. If you are not familiar with that, it is available in the previous module and I suggest that you go and review it. So let's start. To derive the principle of work and energy, imagine that you have a particle as shown in the figure to the right. If this particle is moving in a curved path S, there are two coordinates that are needed to describe its motion. One in the tangential direction, the other one is the normal. I'm going to write Newton's second law for the tangential direction, which is the equation shown to the left. So summation of forces in the tangential direction equals MAT. I also know from kinematics, and you should know as well, that AT equals to V dV ds. Basically, I'm going to take this expression and plug it in here. Okay. Now, if I do so, I'm going to end up with the following expression, that Ft should equal to mv dv ds. What I will do now is that take this operator, ds, and add it to this side and integrate both sides. Each side will have the integral limits based on the integral operator. Therefore, summation of forces of Ft times ds will be integrated from S1 to S2, and mv dv will be integrated from V1 to V2. So the left-hand side, basically, from the previous module, you know that this is the expression for the work done by the forces. The right-hand side is going to give me a new expression, which is the kinetic energy, and you are going to represent it by the letter T. So this will be T2, this will be T1. Okay. It is important to note that the work done by the forces, you can see on the left-hand side, is done by tangential forces only, which confirms the definition of a work done by a force in the previous module, that the force has to be in the same direction of motion. Now, I'm going to take this T1 and plug it in here on the left-hand side to rearrange the expression. Therefore, as a summary of these steps, we said that this is the definition of the work done, and the kinetic energy will be called T, and when I move T1 to the left-hand side, I end up with this expression. Okay, now this is for one particle. If I happen to have a system of particles, then basically what I am going to do is that I will add a summation for these particles. That's it. So let's say I have here, this is particle A and particle B. And these are internal forces, and these are external forces. So first thing is that I have to tell you that this equation, I recommend that you write it for the whole system, for all the masses and the particles that you have, meaning that summation of T1 will equal to half MA VA1 square plus half MB VB1 square, and so on. And the same thing can be done for T2. Okay? Now, one important thing behind the reason why I recommended that you write this for the whole system, that usually when you write it for the whole system, internal forces cancel each other and do not give you any work. Now, if you are going to write this principle of work and energy for particle A alone and for particle B alone separately, then you have to include the internal forces in each one. And you can see why this is a problem, because you are adding more unknowns, you are adding more steps into the solution. Whereas if you write it for the whole system, it is one equation, and in the same time you are cancelling all internal forces. And they have one example that we are going to solve next that will highlight this advantage of writing it for the whole system. So just to summarize, the principle of work and energy is only this equation, where we know that this is T1, this is T2, and the work done between position 1 and position 2 could include external forces, or could include the work done by a spring force, or the weight, or friction forces. Remember that the work done by a force is positive if the force is in the same direction of the displacement. The work done by a force is negative if the force is in the opposite direction of the displacement. Therefore, you can see that the force done by the friction is always negative. Work done by the weight depends, could be positive, negative. Spring is always negative. And then applied forces, it depends on the direction of the applied force. So let's start with the first problem. Block A has a weight of 60 pounds and block B has a weight of 10 pounds. The coefficient of kinetic friction between block A and the inclined surface is 0.2. Neglect the mass of the cord and the pulleys. Find the speed of block A after it moves 3 feet down the plane, starting from rest. Now, one thing that I would recommend to students, because this is one of the sources of many common mistakes that students do, is that whenever you have a rope and pulley system and you're going to use it, and you know that you're going to use it in this problem because block A moves 3 feet down, therefore you need to find what is the movement of block B, and the same thing for the velocity. So start with the rope and pulley system, because this will help you in the sign, when you write the sign of the forces and the displacement later on will be related to this one. And I'm going to explain it once I reach that part. So let's start with the rope and pulley system. Block A, you can move up the inclined surface until you find a fixed datum. And this is my fixed datum in this problem. And SA is defined downward from the datum towards the object. So SA is positive, downward from the datum towards the object. S is always positive from the datum to the object. Same thing with SB. I move upward, I find a fixed datum. SP is positive downward because this is the direction from the datum to block B. So for SA, I have 2 segments. For SP, I have 1 segment. So let's write the equation. I'm going to have 2SA plus SB should equal to L, the length of the cord. The first equation that I'm going to derive out of this is the change in the displacement. So it's going to be 2, so this is the first one, 2 delta SA plus delta SB should equal to 0 and not L, because L does not change. The length of the cord remains constant throughout the whole problem. Therefore, delta L will be 0 in this case. Now from here, I can substitute the values. 2 will be multiplied by block A. If you read the statement of the problem, block A, after it moves 3 feet down the plane. So it is moving 3 feet downward. Is it positive or negative? Well, it's positive because SA is positive downward. So it's going to be 2 multiplied by 3 should equal to minus delta SB. This gives me that delta SB should equals to minus 6, or basically 6 upward feet. Because SB is positive also downward, therefore minus 6 will indicate that it is 6 feet moving upward. So it is 6 feet, as you can see here, moving upward, or minus 6. The second expression that I can get is to differentiate the first equation with respect to time, and you get velocities. So you can write 2 VA plus VB should equal to 0, which will give me that VB should equal to minus 2 VA. And this is an expression or a relation that I'm going to use later as I solve this problem. Okay, so I'm done with my kinematics. Now let's go to the free body diagram. I need to draw the free body diagram of the 2 objects. So block A, okay, first of all I have the tension. Since I have 2 segments attached to it, I'm going to say 2T. Since block A is moving downward, therefore the friction will be acting upward, and it's going to be mu times NA, and I'm just going to add NA in here. So this is NA And finally, I have the weight of block A, which acts downward. Now, we are given that the angle is not given, but the relation here is given for this triangle, and it is 5, 3, and 4. Now, the weight has two components, and I need to open these two components. This is the first one. This is the second one. So I need to know which is the 5, the 3, and the 4. The 5 is simple. This is the 5. But I need to know which one is the 3, which one is the 4. Simply follow this procedure always to help you. So this is 5, this is 3, this is 4. And in the case of my free body diagram, I have this line, I have this one, and I have this one. This is 90, and this is 90. Okay, and this is my 5. I need to find which one is the 4, which one is the 3. For the sake of discussion, let's say that this angle is theta. I need to find which one is theta. Is it the upper angle or is it the lower angle? To do this, just pick two sides of the triangle and find on the other triangle the two lines that are perpendicular to those. I'm going to repeat this. First of all, pick two lines from the first two sides from the first triangle. I'm going to use this one. I'll put one dash in there, and I'm going to use this one. I'm going to put two dashes. So let's look on the other triangle and find the lines that are perpendicular to those. Okay, so the one where I have one dash, which one is perpendicular to it on the second triangle? It's this one, right? So that one is the inclined surface on the left-hand side. The triangle on the right, this is the one perpendicular to it. And if you look at the two dashes, this is a horizontal line, so this one, the one perpendicular to it. Therefore, the angle between them should be theta. In this case, the angle was between the 5 and the 4, therefore this is the 4, and I'm left with the 3, and that's it. So this is a very neat trick to solve this issue whenever you have it. If you don't need this and you can figure it out directly, then use whatever that makes you feel happy. Second free body diagram for block B, I only have one tension upward and I have the weight of block B downward, and that's it. Now, next thing is to apply the principle of work and energy. Always start by writing the general equation, and then from there you go downward by writing all the terms. I always recommend that you follow all the steps, write everything, even if it looks or sounds trivial to you. It is important to organize your work to avoid any silly mistakes, which are common, by the way. So, principle of work and energy, summation of T1 plus summation of the work done. So, plus summation of the work done between 1 and 2 should equal to summation of T2. Now, right, since I have a big problem with two different masses or particles or objects, then I'm going to write every one of these separately rather than cramping them all together into one huge equation. So I'm going to write summation of T1 equals to half MA VA1 square plus half MB VB1 square. Now, if you remember, if you read the problem statement, it says starting from rest. Therefore, the initial velocities in this problem are all 0, and T1 becomes 0. Now, let's look at summation of T2. I'm going to write, it's basically going to be the same expression, except that instead of 1, I'm using 2. So it's going to be summation of T2 will equal to half MA VA2 square plus half MB VB2 square. Okay, now I already have one relation that VB equals minus 2VA. So therefore VB B square will equal to 4 VA square, right? So that's basically what we have in here. So go back and substitute this one into this equation, okay? So we have the following. So it's going to be equals to half NA VA2 square plus half NB, and now remember that VB equals to, as we mentioned before, that VB equals minus 2 VA. The minus, when you take the square, does not affect anything, becomes positive, and you get 4 VA, okay? Therefore, you get 4 VA, so when you take it to that part, it's going to change this part to you. So you end up with 4 VA square. Okay, so we'll leave this one here. And then finally you have summation of the work done between 1 and 2 equals 2. So let's start with the first thing, with the block A. What do you have? Let's start with the weight. The inclined component of W, which is this one, is going to give me work, but this one, the perpendicular will not give me work. So I'm going to take the other one. Did not fill these. So this is basically 3 and 4. So I'm going to take 3 over 5. That's the component that's going to give me work. And it's positive because it's in the same direction of the work done. So if I take that one, it's going to be, I'm going to open a bracket. So it's going to be 3 over 5 WA. And then I have the tension, which is opposite to the direction of motion. So tension is opposite to the direction of motion. So we finished the work. So T2 tension will be minus. So it will be minus 2T. I'm going to multiply them all by the displacement at the end. And then I have friction, which is also negative, as we know. So it's going to be minus mu NA. So as I mentioned, the friction force is always going to be negative. So minus mu NA. All of this is multiplied by delta SA plus, open a bracket. Now I have the tension is upward, the weight is downward. Now this is where the confusion happens with students, and that's why I always recommend that you start with the rope and pulley system. One way, and this is the best way to avoid any mistakes, is that to follow the same sign convention that you used in your kinematics. In this problem, SA was positive downward. SB, if you look in here, was positive downward. All of them downward. So take downward as your positive. Therefore, if you look at the free body diagram, WB is moving down. Therefore, it's going to be positive. T is moving upward. It's going to be negative. So I'm going to say, here I have WB minus T. Sorry, I keep doing this by mistake. Okay? So that's it. Minus T, sorry. This is multiplied by delta SP. Now, let's look at the problem. How many unknowns? Remember, this is a scalar equation, and I wrote it for the whole system. Therefore, I can solve for only one unknown. Only one unknown. So, summation of T1 is 0. Does not bother me. Summation of T2 has 2 unknowns, VA and VB. But because of the kinematics, I can rewrite them as, forgot to write 2 here. I can write them as one unknown. So I have only one unknown in here. Let's look at the work done. The weight is known. 2T is unknown. NA is unknown. This is known. This is known. This is the same unknown. And this is known. Now, NA, I can find it from Newton's law. I can do summation of forces. I will come to that. But let's look at the tension. It's an internal force. And remember, I told you that if you write the principle of work and energy for the whole system, you do not need to include internal forces because they cancel. The reason I included the 2t here is just to prove this to you. Remember that from kinematics that SB equals minus 6 and SA equals 3. So let's look in here. Just bear with me and let's look at this. I have 2t and I have SA multiplied. Okay, so I'm going to get minus 2t multiplied by 3, which will give me minus 6t. Here I have minus t multiplied by delta SP. If I multiply these two, it's going to be minus t multiplied by minus 6. You end up with 6t. So 6t, the magnitude is the same, the sign is opposite. These two will cancel when I go to the final equation. Therefore, these two will cancel each other, which is what I promised you at the beginning. If you take the whole system, internal forces cancel. And I included it here just for the sake of discussion. When you solve these problems, you do not need to write the tension into the equations because it will cancel eventually. Okay, so I just wrote it here just for the sake of the discussion to describe it to you. Okay, now let's go back. Since we have everything, go back to the problem just to read it. As it says here that you need to find the speed of block A after it moves 3 feet down the plane. So everything is ready now. I'm going to write a final thing, which is to find the value of NA. This is the free body diagram for block A. I need to find NA. So I'm going to take summation of forces in the Y direction. So this is Y. I'm going to take this as positive. Summation of forces in Y should equal to MA AA in the Y. And this equals to 0 because I have no acceleration in the Y axis. And this will give me that NA minus, remember this one, we already did it. We said this is 5, this is 3, this is 4. So it's going to be NA minus 4 over 5 of WA equals 0. And this basically gives me that NA should equals to 4 over 5 WA. And that's it. That's all I need. Okay. Now go back and write the final equation, execute everything. As we said, if you remember, summation of T1 equals to 0. Summation of T2 is equal to, just to go back to remind you of that one, we have half MA VA2 square plus half MB 4 VA2 square. So I'm going to take these two and do it in here. So I'm going to have half MA is not, I don't have the mass, I have the weight, which is 60 pounds. So to get the mass, I divide by the gravity, which in British unit system, it is 32.2. Okay, so half M and then multiplied by VA2 square. Okay, now you have again plus, okay, half MB, which is basically 10, which is the weight, over 32.2, okay, multiplied by 4, okay, and multiplied by 4, this is multiplied by VA2 square, okay. Now, this should equal to, if you equate everything together, you have VA is a common factor, you have the half as a common factor, so you have 40 plus 60, you get 100 over 2, you get 50. So you get 50 divided by 32.2 and 100 over 50 over divided by 30. So you end up with 1.55 for that one. So you end up equals to 1.553 VA2 square. Okay. Now, next step is to find the work done between 1 and 2. So, work between 1 and 2. Remember that we do not have the tension any longer. So, it's going to be 3 over 5 multiplied by the weight, which is 60, minus to remind you. So this is WA, we finished it. 2T is cancelled. Now I have mu times NA. And NA equals 4 over 5 WA. So I'm going to write the mu, which is first 0.2, okay, multiplied by NA, which equals to 4 over 5, multiplied by WA, which is 60. All of this is multiplied by 3. Okay, plus have the weight of block 2, which is 10. Okay, and I have no tension. So this 10 is multiplied by minus 6. Okay. Now, this should equal to, if you carry this calculation, it will give you 19.2. Okay. Now, write the whole equation. Now I'm going to write 0 plus 19.2 should equal to 1.553 VA2 squared. This should give me that VA2 should equal to, you divide 19.2 divided by 1.553, and then you take the square root of that one, you get the final answer, which is 3.52 feet per second. So feet, again, let's erase this one. So you end up with the final answer, 3.52 feet per second. And this is the final answer. Now, this is a very good example. It covers most of the forces that you can face. It has two objects. It has rope and pulley system. It has some tricks with the sign convention that you want to make sure that the signs are correct. And one suggestion that I would recommend that you would go and solve this again by separating A and B. Now, even though I said at the beginning this is not recommended, I would recommend that you solve the whole thing as one system, but I want you to experience solving this by separating A and B and including the tension in that case, just to see how lengthy it becomes. Once you do this yourself, you will appreciate solving this as a whole system, because many students, even though you would explain it's a whole system, when it comes to exams or solving projects or something like that, by default they forget and they go and separate the system and they are not used to it and they get some mistakes. So this is my suggestion for you. Now we have another quick example just to explain the idea of springs. In this problem, we have springs A, B, and CD have a stiffness of 300 and 200 Newton per meter respectively. So each one has a different stiffness. Both springs have an unstretched length of 600 millimeters. Keep in mind, if you look at the figure below, they are originally at the unstretched length. This is not always the case. Sometimes the problem will say that they have a certain unstretched length, but their initial position is actually compressed or stretched. Anyway, so let's look at it right now. So both are unstretched and they have a length of 600 millimeters. If the 2 kilogram smooth collar starts from rest when the springs are unstretched, so at this position it is at rest and the springs are unstretched, find the speed of the collar when it moves 200 millimeters to the right. It doesn't say to the right, but it's obvious from the applied force. So the first thing you want to do here is always draw the free body diagram. And always when you draw the free body diagram, include all the forces regardless if it does work or not. So first of all, we have applied force equals to 150 Newton. And the angle is given as 30 degrees. I have the weight of the collar. I have a normal force acting on it. And I have two spring forces. Each spring, remember, since the collar is moving to the right, the spring force is always acting on the opposite side of the motion. So it's going to be to the left. So I'm going to have F for spring AB. And in here, I'm going to have F spring CD. Okay? Now, write the principle of work and energy. We have the principal, the principal fork energy. So I have summation of T1 plus summation of the work done between 1 and 2 should equal to summation of T2. Now, since the problem said that it is starting from rest, so T1 should equal to 0. Okay, plus, let's look at the applied force. Since the collar is moving to the right and the force has a component acting to the right, it's going to be a positive work. So it's going to be 150 multiplied by cosine 30 degrees. So this is the component of the force. Now multiplied by the displacement. It is moving 200 millimeters to the right. Therefore, I'm going to write 0.2. Okay. Now, plus. Let's look at the spring force. Okay. Both of them are acting to the left, so opposite to the direction of motion. Therefore, the work will be negative. And if you remember the expression, the work done by a spring force is minus half KS square. Okay, so let's look at spring AB. I'm going to say minus half. The spring stiffness is 300 for AB, so it's minus 300 multiplied by S. Now, what is S? S is basically the amount of stretch or the amount of compression. Okay, so if I look back into this problem, this was originally 600. It moved to the right 200, so it became 800. So the difference between these two is 200. Let's do the other ones while we're at it. So we have 600. When this spring is compressed by moving 200 millimeters to the right, it becomes 400. So the difference is minus 200. Okay, so back to my equation. This is going to be minus half K delta S or S square. So it's going to be 0.2 because I'm writing in meters instead of millimeters. So it's going to be 0.2. Okay, so it's going to be 0.2 square. Okay, that's it. Now let's go to the other spring. I'm going to have plus. I'm going to add it. Now let's look at it. It's going to be minus half. K is 200 in this case, 200 multiplied by minus 0.2 square. And the minus does not matter actually. Okay. This should equal to half mv2 square. Okay. Now, basically this is going to equate everything. Mass in this case, let me write the value of that mass as well. So it's going to be, just to include it while I'm at it, so it's going to be half multiplied by the weight of that one, or the mass of it, it's going to be 2 kilograms. So half multiplied by 2 V2 square. If you solve everything, it gives you that V2 should equal to 4 meters per second. Okay, and this solves the problem. Now, even though it's a simple problem, I like it because it gives you a clear understanding of how to write the spring force. Now, I did use a short cut in this problem because, as I mentioned when I was reading the problem, the unstretched length is the same as the initial position. If you go back to the previous module, I told you that for every spring, I'm going to do it here since I already solved the problem, just to explain it. We said that the work done by the spring force for one spring, I'm discussing only one spring. In this case, let's do AB, for AB only. It's going to be minus, open a bracket, half K S2 square. So I keep getting this mistake. So it's going to be half K S2 square minus half K S1 square. Now, remember I said, what is S1, S2? S1 is the current position 1, and S2 is position 2. Now, S is the amount of stretch or compression. In this problem, let's look at S1, S2. S1 will be the length at position 1 minus unstretched. What is the length in position 1? It was actually 600. Minus, what is the unstretched? It happens in this problem that they are the same. Therefore, I get S1 equals 0. What about S2? Equals length in position 2 minus unstretched. So in this case, I get 800 after it moved 200 minus the unstretched, which was 600. This gives me 200 millimeters. And that's why we use 0.2 in here and the same thing in here. If you have another problem where the original position of the spring, which is this one, is not the same as the unstretched, then this expression will change, this expression will change. Okay? Therefore, as I mentioned, in this problem, I used the shortcut since the unstretched length is the same as the original. Otherwise, you have to use this approach. Okay? So with this, I conclude this section and this module, and I hope that you found it helpful to you, and I wish you the best of luck in your studies. Thank you so much.